Hi everyone, this is Alvaro Montes. It's Snoop Dogg's voice with another interesting video. Today we are going to learn about big O notation, calculating algorithm efficiency. Big O notation is the language we use for talking about how long an algorithm takes to run. It's how we compare the efficiency of different approaches to a problem. Imagine you have a list of 10 objects and you want to sort them in order. There's a whole bunch of algorithms you can use to make that happen, but not all algorithms are built equal. It is simply a way of comparing algorithms and how long they will take to run. A simplified analysis of algorithm efficiency. It considers complexity in terms of input size, and machine independence doesn't consider the machine's hardware, basic computer steps, time and space working storage. Originally used by German theorist Paul Bachmann. O means order of German, Ordnungszahl. N is the input size in units of bits needed to represent the input. General rules ignore constants, considers long-term growth only. 5 and becomes ON. Terms are dominated by others. Ignore lower order terms. Constant time algorithms. O1. Time taken per input size. Constant time implies that the number of operations the algorithm needs to perform to complete a given task is independent of the input size. In big O notation, we use the following O1. No matter how much data you add, the amount of time to perform a task will not change. The quickest type of algorithm. Graph shows increase in time to run algorithms. Constant time O1 big O of 1. X equals 10 plus 5 asterisk 2. Input size X is independent. Doesn't matter. Doesn't affect processing of code / algorithm. So it's O1. Constant time O1 big O of 1. X equals 10 plus 5 asterisk 2. Y equals 20. 2. System. Out. Print X plus Y. Total time is equals O1 plus O1 plus O1 equals 3 asterisk O1. Because we drop constants, we would call this code O1 big O of 1. Constant time algorithms. O1 example. Consider these two bits of code. It doesn't matter what N is above. This piece of code takes a constant amount of time to run. It's not dependent on the size of N. Logarithmic time algorithms. O log N. Logarithmic time implies that an algorithm's runtime is proportional to the logarithm of the input size. In big O notation, this is usually represented as O log N. Next fastest after constant time. Any code that involves a divide and conquer strategy. Binary search algorithm is O log N. Logarithmic time algorithms. O log N example. Logarithm. Basic principle. How many 2 seconds do we multiply to get 8? 2 x 4 equals 8. So the logarithm is 3. We would write this as log pro 8 equals 3. What is important here is that the running time grows in proportion to the logarithm of the input, in this case, log to the base 2. Any algorithm that ignores a proportion of the input data can be considered O log N. As N is 8, the output will be the following. 1, 2, 3. Hey, I'm busy looking at 1. Hey, I'm busy looking at 2. Hey, I'm busy looking at 4. Log base 2 of 8 is 4. Our simple algorithm ran log pro 8 equals 3 times. Because we drop constants, we would call this algorithm O log N. N equals the input value, for example. Number of elements in the array. Linear time algorithms. ON. Next quickest algorithm. Linear time is a concept whereby time is seen sequentially as a series of events that are leading towards something, beginning, and an end, grow directly proportional to the size of its inputs. Linear time ON example. This loop prints numbers 0 to n, y equals 5 plus 20 asterisk 20 / O1. For x in range O, n, / O n, print x. Total time is equals O1 plus O n equals O n. Because linear time O n takes so much longer than constant time O1, it dominates it and effectively becomes irrelevant. Linear time algorithms. O n example. This code runs n times. We don't know exactly how long it will take for this to run, and we don't worry about that. In this second code, the runtime would still be linear in the size of its input, n. We denote linear algorithms as follows. ON. Polynomial time algorithms. ONP. Also known as quadratic time algorithms. Normally denoted by nested for loops. If your array has 10 items and your algorithm is running in polynomial time, you're going to be doing 10 asterisk 10 equals 100 steps. Polynomial time algorithms. ONP example. For x in range O, n, / O n, print x. For x in range 0, n, / O n 12. For y in range 0, n, print x asterisk y, / O 1. 3 nested for loops. ON 3 4, ON 4, and so on. Polynomial time algorithms. ONP example. Polynomial is a general term which contains quadratic n12, cubic n3, quartic n4, etc. Functions. Assuming n equals 8, this algorithm will run 82 equals 64 times. This is an ON12 algorithm because it has two loops. This would become an ON3 algorithm. ON12 is if we were to nest another for loop. This would become an ON3 algorithm. ON12 is faster than ON3, which is faster than ON4, etc. Bubble sort polynomial time algorithm. Polynomial complexity, the more data you have, the more checks it has to make, and the more time it will take to run. Assuming the data in the array going through the algorithm is now already sorted, this algorithm would be considered polynomial ON12. It has two loops. If the data is already sorted, then the complexity will be linear ON because the loop only has to run once. Enter length of array, N. 100 array contains 99 items. I performed 4,950 checks. Execution time 0 minutes, 0 seconds, 0 milliseconds. Note the big difference in execution time based on array length. Bubble sort is not very efficient for larger data arrays. Efficiency decreases dramatically. Enter length of array, N. Array contains 59,999 items. I performed checks. Execution time 0 minutes, 14 seconds, 344 milliseconds. Cost of running time, acknowledging hardware performance as a factor. Big O notation does not consider performance of hardware. Processor speed, memory, usually RAM, bandwidth, latency, storage space, power all have an effect on algorithm speed. Efficiency of the algorithm, of course, still plays a part, but we can't ignore raw hardware performance. O shows how the algorithm will perform based on big and small inputs. If you have learned through this video, don't forget to subscribe, comment, and share to support the channel. My homie Alvaro is a poor developer trying to survive.